This video is part of a series of presentations covering key concepts of multithreading and synchronization. This presentation in specific covers details of using background or detached threads for multithreading certain types of data parallel applications. Recollect that many problems lend themselves to synchronization-free multithreading. These problems are called data parallel applications, and these problems do not require a semaphore or mutex to synchronize the threads. Keep in mind, multi-threaded programs decrease the overall runtime but not the time complexity of the problems. Synchronization-free approaches are fastest or the best solutions that we should always try first, and this is because synchronization essentially forces parts of a program to run in single-threaded mode, which decreases or degrades the overall performance of multithreading. So we want to try and do synchronization-free approaches as much as possible. There are two categories of synchronization-free programs that we have already seen in the previous presentation. First one is data parallel applications, where each thread runs the same algorithm or solution, but the input data and output data is going to be different. The second type is called task parallel applications, where each thread runs a different algorithm. However, the input data for each thread is the same, but the output data is different, or they're stored in different locations, so they do not have to have any synchronization. In this presentation, we are going to physically focus on the one-to-one data parallel application where each thread operates on one input and generates one output. So that means for each input that is given to us, threads will operate on them, and for each one of those inputs, there will be a corresponding output that will be generated. However, in this series of presentations, we are going to focus on a specific type of problem where each thread is going to still operate on one input, but it's going to work with input-output streams instead of just data values. And also we are going to focus on problems where the main thread does not require the results from the other threads that it is going to start. That means it doesn't have to actually wait for the other threads to finish. And of course, we'll create separate threads for each one of the inputs that we want to process. Keep in mind, we have so far used a standard two-loop pattern for processing and working with threads. The first loop essentially spins up all of the threads that we want to use to solve a problem. And then the main thread waits for the threads to join. That means it waits for the threads to finish. And typically we'll use this type of a thread called foreground thread when we do want the results from the threads that we're spinning up. So for example, here when we're doing the prime checks, we want all of the results from all of the threads to be available before the prime check methods finish. So we wait for all of the threads to finish or wait for all of the threads to join. This kind of operation is called foreground threads. Here, foreground threads are used when the results from the threads are needed in order to proceed further. And of course, we must call the join method on the foreground threads in order to reclaim the threads. Otherwise, threads will not operate correctly or the operating system will throw an exception. Alternative to foreground threads are background threads. These threads are also called detached threads. They are used in algorithms where the results from the threads are not really needed in the main thread. This might be because threads independently generate results, and these types of background threads are used for different types of tasks like garbage collection, monitoring, logging, transaction processing, etc. So there are lots of different applications where these detached threads or background threads are beneficial. Here, detached threads are created by calling the detach method right after a thread is constructed. Keep in mind, with detached threads, you cannot and you should not call the join method on these threads. Instead, detached threads are automatically terminated when either the thread method completes or when the main program ends. So that either of these two cases, a detached thread will normally terminate. That means the thread method finishes all of its operations, then the detached thread automatically is terminated. Or when the main program ends, even if the background thread is running, the operating system will forcibly stop these threads so that the program will successfully complete. Now let's look at an example application, let's start with an example of a single-threaded web server which accepts connections from multiple clients, but it uses a single thread, so it's going to process one request at a time using a single thread. So let's look at a method called, assume a method called serve client is defined for us already. So the serve client method is going to read some requests from an input stream and write the response from the web server to a given output stream. So in our web server method, we are going to use a boost acceptor to streamline and simplify socket operations for us. So this web server is going to run forever, accepting and processing connections, which is what normally web servers do. Here we're going to wait for a client to connect to our web server. So we're going to accept a connection from the client. And then we're going to have the serve client helper method process the input data from the client and then generate output back to the client. And this loop runs over and over. Let's make sure we have a visual of how this web server works. So here we have a program running. So we can have multiple clients that are interacting with the web server, maybe thick clients, that means these are dedicated apps, or thin clients, which could be web browsers. So these clients will make connections to our web server using TCP sockets, and they'll all generate HTTP requests to our web server. So the web server can get multiple requests, but it runs only one thread, so it'll process one request at a time and generate the response back to the client and then move on to the next request. So this is how a single-threaded web server would process requests one at a time. Keep in mind there are several disadvantages here. Every client may have to wait for slower clients to have their request processed, so they have to wait to get a response from the web server, so it can take considerable time. Second, this approach of using a single thread does not utilize the hardware that might be available on the web server. So the hardware could support multi-core CPUs, and you could have multiple CPUs on the server. So we could have actually processed many requests simultaneously, but the single-threaded solution does not enable us to effectively use the hardware. And of course, keep in mind each request in this example operates independently using its own socket connection, so there's no shared data. And of course, notice that the main thread does not really need any results back from the threads, because the threads simply read data from a client and write data back to the client. So the main thread is just orchestrating the process of accepting connections and having the serve client helper method process data from the clients. So now let's see how we could multi-thread this type of an application. So here in our multi-threaded version, it's going to accept connections from multiple clients, and then it's going to spin up a separate background thread for each one of those connections. Okay, so we're going to assume we have the same serve client helper method that we looked earlier. We're going to create our run server method, and we're going to make modifications to our run server method. Again, of course, the multi-threaded server is going to run forever like all of the other web servers do. Here, first, we are going to create a client connection as a dynamic or a shared pointer. And this is done because normally when we run these client objects, these client connections are created and destroyed in each iteration of this while loop. So, but we do not want this behavior because we want these client connections to persist beyond the scope of this while loop, so that we can pass these client connections to threads so that threads can operate on it. So intentionally, we are going to create a shared pointer using dynamic memory, and this shared pointer is automatically garbage collected and closed once the threads finish using it. So that's the idea of the shared pointer here. Next, we're going to accept the connection just like we normally did from a client. And then once we get a connection from a client, we're going to spin up a thread to actually process the request from a client on a separate thread. Notice that here, instead of using a thread method, we're just specifying a lambda. And the lambda is essentially calling the serve client method like we did in the single threaded mode, except it is calling it from a separate thread. The lambda takes the client connection as a copy. This is to ensure that the shared pointer is correctly passed, and the shared pointer tracks how many copies are there to the connection to the client. And once this thread method completes, when the thread finishes, all of the references to the client will be complete, and the client connection will be automatically closed by the shared pointer that we are using here. So it makes the shared pointer makes this multi-threading a little bit easier for us. And of course, once the thread is spun up, we detach this thread. So when we detach the thread runs asynchronously as a background thread. And we do not have to wait for these threads to finish, because once the thread method is done, these threads are automatically reclaimed by the operating systems. So this server can now go on to accepting connections from other clients, and the main thread does not need to wait for the threads to finish. And of course, one other advantage here is slower requests do not stall or hinder or interfere with other requests, because each one is running as a separate thread. So now let's have a mental model how this web server works. So we created our web server, and we are going to accept multiple connections from clients, and they're going to send those requests to us. Multiple threads operated concurrently on it and send requests back to the clients and close the connections. So here we're able to do multiple requests simultaneously. From a client perspective, we can see the impact here. So let's say we are running a multi-threaded version of the server. You'll see that it processes one request at a time. So given 6 requests, it's going to take about 6 seconds or slightly more than 6 seconds to process these requests and load the web page as a whole. Because here we assume that each request takes about 1 second, we have 6 requests, and the total time taken is about 6 seconds. Now, if we were to multi-thread this server, notice here multiple requests will be processed simultaneously by the web server, and the total time to process these requests decreases from about 6 seconds down to about 2 seconds. And if you refresh these web pages, you will see that requests can be processed in about a second, because all of these requests run simultaneously, thereby accelerating the time taken to load and render web pages. This is a key advantage of multi-threading, and of course here detached threads make it very easy to develop this kind of efficient, effective solutions for web servers, database servers, and other online transaction processing systems. And this enables effective utilization of large hardware servers by using multiple detached threads that run asynchronously, utilizing the hardware, performing different operations, and sending results back to the clients. So here's a quick recap of what we're learning in this series on multi-threaded programming. We've already seen the basic ideas of threads and how to do it in C++ and how to measure the performance of threads. We saw the idea of race conditions, and we are currently studying how to do threading as data parallel, task parallel applications, but these applications do not require any synchronization. So we've seen both foreground threads, and now we've seen background threads. The next parts in the series will focus on synchronization and threading. Hope you found this presentation interesting. Don't forget to check out the other parts of presentations in this series.